Hi, my name is Mr. Ray, and this is the first video in a series of videos on the climate narrative and science. We're going to examine the climate narrative, and we're going to do it in light of real science. And the first video is that cows are not a threat to climate, and I'm going to prove it to you. According to current climate theory, methane from cows and nitrous oxides from fertilizer and ammonia are powerful greenhouse gases that threaten to overheat the planet. And so the proposal that is being suggested is that we kill off cows, stop using fertilizer, and eat insects, etc. So first thing we're going to do is look at where these ideas come from. And we're going to examine them, see if they stand up to scientific scrutiny. The chart that I'm going to use to do this is this radiation transmitted by the atmosphere, and it's found at this location on the internet. You can really use any chart of radiation that's absorbed as long as you have the gases that are absorbing it and the wavelengths where it's absorbed, and you can compare those wavelengths the way that I'm going to do. So here's the chart, and you see at the top of the chart, this is the red side over here. This is radiation coming in from the sun, okay? And then this is radiation on the right, is radiation coming out from the Earth. So this is what the Earth is giving off, and the Earth gives off all the radiation that would be under these curves right here. Okay, and the part that's absorbed is shown on the charts below, and the part that gets through is shown right here. This is the blue, the amount of radiation that comes out of the Earth and is transmitted into space. Now if we look down here, we have radiation absorbed by water vapor. So this is all this area shaded in is radiation absorbed by water vapor. And down at the bottom it tells you what the wavelengths are, the wavelengths of radiation. Short wavelengths down here that are 0.2 micrometers to 1 micrometer to maybe 1.2 or 3 micrometers are the radiation that's coming in from the sun. Very short, high energy wavelengths. On this side, you've got longer wavelengths, and that's wavelengths of heat radiation given off by the Earth. And so up here you can see it's infrared radiation. So a lot of the radiation that comes from the sun is in the visible range, some UV over here, and also some infrared here. What's given off by the Earth is heat radiation in the infrared side over here. So all the wavelengths are down below, and then you can see the various types of gases that absorb heat radiation coming off the Earth. And so we have carbon dioxide here, we have water vapor here. Water vapor absorbs these wavelengths, absorbs some here, and so on. Carbon dioxide will absorb these wavelengths right here, plus a few up here. Oxygen and ozone absorbs a little bit of wavelength right there. Methane absorbs this wavelength, and this wavelength right here. Nitrous oxide, that would be the nitrous oxides from fertilizer, absorbs energy right here and right here, and a tiny bit here, and then we've got Rayleigh scattering, which only absorbs up in this area. So you have all these various greenhouse gases absorbing, and then this chart right here shows the total absorption of all of them put together. How the energy that's being absorbed as it's coming on this side as it's coming off the Earth. So once again, the wavelengths on the left are coming from the sun. The wavelengths on the right are coming out from the Earth. This is what the concern is about. This is radiation, heat radiation that is coming out off the Earth, and these are the greenhouse gases here that are absorbing that radiation. So the blue stuff makes it to space, but this area in here and this area in here gets absorbed by the greenhouse gases. So that's radiation being absorbed as the Earth is trying to give off heat. So some of it is absorbed and that means that the heat is absorbed into the atmosphere and into those gases. Greenhouse gases and what they absorb are below. That's this area. Methane and nitrous oxide. You'll notice methane right here, nitrous oxide. Methane from cows, okay, and nitrous oxide from fertilizers and ammonia. And you can see that they absorb near the 8 micrometer wavelength. So if we count from here, this is 10, 9, 8 right here. You got nitrous oxide absorbing there, methane absorbing there. And if we follow it up, we'll see that there's a significant amount of radiation given off by the Earth in those wavelengths. So everything from underneath this curve would be given the Earth trying to send that heat into space, and it's being intercepted by methane and nitrous oxide. And that's the big concern right there around the 8 micrometer wavelength. When you get out to this wavelength of nitrous oxide and you follow it up, there's almost no radiation being given off by the Earth. So there's very little. So this is really not the concern. This wavelength out here is not the concern. The main concern is this number 8 wavelength right in here for methane and nitrous oxide, 8 micrometer wavelength. Okay, so here's a close-up again. Right around the 8 micrometer wavelength, you've got nitrous oxide absorbing that little bump right there, methane absorbing that little bump right there, and as you go up, you can see that there's quite a bit of radiation coming off the Earth at that wavelength. Now, when we look over here on the left, we see a scale. This is the percent of the radiation that's being absorbed. And so in this area right here where it takes up the whole chart, that's 100% of the radiation being absorbed. So this is the total combined radiation that's being absorbed, and it goes from 0 to 100%. On each one of these bars, they are also from 0 to 100%. And so you can see right here, water vapor absorbing 100% of the radiation at this wavelength. Okay, so this is the same scale as this, just the one that represents the total has been expanded and made to look bigger. But this water vapor chart right here, this is from 0 to 100%. This carbon dioxide chart, 0 to 100%. Each one of these individual bars is also 0 to 100% here. They're just smaller. They're just made to look smaller than this one right here. This is made to look different because it represents the total of all of them put together. All right, we'll get to that a little more detail in a minute. But once again, the 8 micrometer wavelength, this is the big concern, the absorption of fertilizer here and the absorption of methane from cows right here. This slide I've lined it up so that you can see about the 8 micrometer wavelength. You can see how it goes right through the nitrous oxide absorption. The methane absorption's right around it, water vapor absorbs right around it, and then the total is right here, straight up. So there's a straight line to show you that all of them line up on the chart at that wavelength. So when we look back at that chart, we're going to see near the 8 micrometer wavelength, water vapor is absorbing about 90% of the heat radiation coming off the Earth at that wavelength. We're going to see water vapor absorbing about 90% of it. Methane will absorb about 30% of it. So if we add 90 and 30, we should be well over 100, correct? Okay, so let's take kind of a look at this. We'll get a closer look at it in a second. But if this chart is 0 to 100 on methane. So if we look at this peak comes up maybe 30%. Okay, so that's where I get that from. So methane will absorb about 30% of the radiation coming off the Earth. We look up here, water vapor, and right there at the 8 micrometer wavelength, that's about 90%. Okay, and we'll get a close-up on how much that is on the next slide. Okay, I've enlarged it now so that you can see it better. Here's water vapor absorbing. Okay, here's the around the 8 micrometer wavelength. we see that I've taken this out and slid it up here so that you can see them both together. But you can see that's about 30%. That level right there of methane is absorbing about 30%. And you look at water vapor in the same region here, and you can see there's a little bit of a gap. It's absorbing maybe 90%. Okay, so 90% absorbed by water vapor, the rest of it absorbed by methane. And if we were to take this methane and add it to this water vapor, our total should be well over 100. It should fill it right up, maybe out to here. Okay, so this whole thing should be filled in the total. If we take the absorption of methane and add it to the absorption of water vapor, that should fill this up to 100%. Okay, so we saw near the 8 micrometer wavelength, we got water vapor absorbing about 90%. We're going to look back at it again and see the nitrous oxides also absorbing about 40%. So between water vapor absorbing 90, methane absorbing 30, and nitrous oxides absorbing 40, we should easily add up to 100% in the total. Okay, so here it is. I've done the same thing to the nitrous oxide. I took this same section of methane. I slid the nitrous oxide up here. You can see that that's around maybe 40%. Okay, again, water vapor is absorbing up to, on this side, water vapor is absorbing 100%. But right here, this little gap, this is where it's about 90%. And so if we take this nitrous oxide and this methane, and we add that and add that, it should put us well over 100% in the total right there. And you can see how all of these line up right with this little gap area right here. Okay, so here it is. We see nitrous oxide here, we see methane here, we see water vapor here. And if we add all three of those together for the total, what happened here? Notice this gap that was here before is still here in the total. What happened? Well, it's not 100%. So what happened? Shouldn't they add up to reach the total? By the way, the total, as we said before, has been stretched vertically to look different. But those three did not add up to 100%. What happened? Again, magnified, this piece right here, and this piece right here, and the water vapor right here should fill in the total. But the only thing that's happened is we've got the exact same gap here, stretched vertically. Okay, it looks like this looks like it's bigger, but that gap's still there. This should have added up, this block right here and this part right here should have added up to knock that little gap out. That should be 100% right there. But you can see that if you take this, what's in water vapor here, and you stretch it vertically, it's going to look like this. And it almost looks like there's no change between what the water vapor is absorbing and the total. It's because we still only have 90% absorbed. We have 90% absorbed here, and we have 90% absorbed here. And we've still got this little part that runs down the side there. Okay? And it seems like methane and nitrous oxide added to this should make it 100%, but it doesn't. And that is the big problem with the climate narrative about methane and fertilizers. Methane from cows and fertilizers and nitrous oxides from fertilizers. It doesn't add up to 100% because it doesn't work that way. And so here's an analogy, okay, to show you how it really does work. Okay, so let's say there's an apple tree, it's got 100 apples on it. Now I'm fairly tall, so I can reach 90 of them. My wife could reach about 70, and my daughter can reach about 80 of them. Together, how many do you think we could pick? Now remember, this tree's got 100 on it. We can't climb it, we can't boost, and we can't use tools, just standing and reaching. I can reach 90, my wife can reach 70, my daughter can reach 80. You might think together that we could pick 90 plus 70 plus 80, but remember the tree's only got 100 apples on it. okay, and the highest we can reach is 90. That leaves 10 apples at the top that no one's going to reach. So 90 plus 80 plus 70 is 240. Can we pick 240 apples from a tree that only has 100 apples? No, we can't. Can I or my wife or daughter reach any of the 10 at the top? No, there's going to be 10 at the top that nobody can reach. Now, if I were to come to the same tree and come by myself, how many apples could I pick? Well, we know that I can reach 90 of them. So the answer in both cases is that if we come to this tree, all three of us, or just one of us, or myself alone, if I come to this tree alone, or if I come with the other two people, we're only going to be able to pick 90 of the apples. There's 10 that no one can reach. Now the apples don't care if one person or three people are picking them. If I'm alone, I'll come home with 90 apples. If the three of us go, I'll personally get less than 90 because my wife and daughter are going to pick some that all of us could reach. But we still come home with a total of 90. Now it works the same way with molecules and radiation. If water vapor is all by itself, there's 10% of the radiation it can't reach or absorb. You see that right here. Water vapor absorbs all of that radiation. It's like picking all the apples except for a few at the top. The water vapor can reach all this radiation and absorb it, but it can't absorb this little bit at the top. Even if all the methane and the nitrous oxides are eliminated, water vapor is still going to absorb that 90%. So even if you took away all the methane, all the nitrous oxide right here, water vapor is still going to absorb 90%. If methane and nitrous oxide are included here, you'll notice it doesn't add together. It doesn't make it any higher. These can only reach up to 30. Methane can only reach up to about 30% here. Nitrous oxide can only reach about 40%. And they do not add up with the water vapor reaching 90%. What's happening is methane can't reach the energy in this area. Nitrous oxide can't reach the energy in this area. Water vapor can reach more than both of them. And so even if water vapor was all by itself, it would still be absorbing that 90% in the total. The total is unchanged by the presence of methane and nitrous oxide. Again, magnified so you can see it better. Nitrous oxide absorbing this much radiation, methane absorbing this much radiation, water absorbing this much radiation, okay, and they do not add together. They don't add together because we're still got a total of 90% of the radiation absorbed in the total. And the reason for it is this, or here's what's happening. This stuff was measured in the lab. So in the lab, nitrous oxide alone, all by itself, absorbs this much. Methane all by itself absorbs this much radiation at these wavelengths. Oxygen and ozone absorb this much. Carbon dioxide absorbs this much. Water vapor alone absorbs this much radiation. Put together, these cannot absorb more than they do. In other words, water vapor can absorb 90% of it. It's like picking apples off the apple tree. Water vapor can reach 90 of them. Methane can reach 30 of them. Nitrous oxide can reach 40 of them. Okay, and put together, they can only still reach 90. There's 10% of it up here or so. Maybe it's 5%. It's hard to tell how big that gap is. But maybe there's 10% up here that none of them can reach. That's going to escape, whether they're here all together or in the total, whether they're here all together or whether they're here or whether they're absorbing separately. There's still a maximum of 90% that they can reach, and methane and nitrous oxide do not add anything to what water can absorb. So radiation doesn't care if one type of greenhouse gas or three types of greenhouse gas are absorbing it. Once some of it gets absorbed, it doesn't get absorbed twice. That's just like the apple picking. Once I've picked a few of the apples, or my wife or my daughter have picked a few of the apples, those apples are gone. They're not gonna get picked twice. And the same thing with the radiation here, whether methane absorbs it or nitrous oxide absorbs it or water vapor absorbs it, it's not going to be absorbed more than once. So water vapor, if it alone will absorb 90% of that radiation, and methane can only absorb 30 and nitrous oxide can only absorb 40, there's always going to be 10% of that radiation that gets through. And as long as water vapor is present, there's going to be no change in the amount of radiation. Please look at this chart. Please understand this chart. Altogether, even if you start with just water vapor, you're going to absorb 90% of the radiation. If you add methane and add nitrous oxide, the total doesn't change. It doesn't get greater than 90. It's just like picking apples on the apple tree. Okay, so the presence of methane and the presence of nitrous oxide do not change the amount of radiation that's absorbed, the amount of heat that's absorbed coming up off the earth, because water vapor is present in the atmosphere. As long as water vapor is present in the atmosphere, methane and nitrous oxide will have no additional effect to the amount of heat that's coming up off the earth and being absorbed. That heat is either going to be absorbed by water vapor, by methane, or by nitrous oxide, but it's not going to be absorbed by nitrous oxide and methane and water vapor. In other words, it's not going to be absorbed 3 times. It's going to be absorbed once. If water vapor is all by itself, then water vapor will absorb all of it. If methane is present and nitrous oxide is present, then it's going to absorb some of that radiation. Water vapor is going to absorb the rest of the radiation, but the total does not exceed what water vapor can do all by itself. Now, I know I'm repeating myself, but I'm trying to help you understand this and help other people understand this. And I hope and pray that our leaders will understand this before they do drastic things that are going to have no effect on the climate. The radiation absorbed by each gas is not added together to get the total, and you can see that in the chart. This plus this plus this does not add up here. Water vapor alone achieves this, okay? And methane and nitrous oxide add nothing to it. The total is derived from combined overlapping. If you think about the apple picking analogy, we overlap 90% of that apple tree, but there's 10% of it that none of us can reach. And so we are going to get a maximum of 90 apples off that tree, no matter how many of us go to pick it. Okay? It's combined overlapping. It's not adding together to get a total. It's a combination of what's overlapping, and since there's overlapping down here, okay, it doesn't add to the total. When the absorbed radiation overlaps, it doesn't increase the total that it's absorbed, because the same radiation can't be absorbed more than once. It can only be absorbed by water vapor or methane or nitrous oxide in these areas that are the same between the 3 of them. Okay, it can only be absorbed by one of them at a time. Okay, and so the total never exceeds the 90% that water vapor can do all by itself. Okay, and just in case you missed it, here's methane, okay, and you can see it's totally overshadowed by water vapor. Anything that methane can absorb, if methane's not there, water vapor is going to absorb it. Okay, so methane doesn't add anything to it. It's just simply that this same radiation that water vapor would absorb by itself is now divided up between some being absorbed by water vapor, some being absorbed by methane, and some being absorbed by nitrous oxide. But without nitrous oxide, without methane, water vapor would still absorb that same amount of radiation, so that the total remains 90%. In this area of concern. This is the area of concern for it. If you look back here, nitrous oxide absorbs a tiny bit right here, but if you follow that up, well, look at that. Carbon dioxide and water vapor overlap nitrous oxide. So fertilizer in this region and are in this wavelength, and this wavelength is totally overlapped by what water vapor would do even if it wasn't there. So nitrous oxide from fertilizer is not adding anything to the absorption of heat coming off the earth. Methane is not adding anything to the absorption of heat that is being absorbed by water vapor as it comes off the earth. Methane isn't adding to that at all. It's absorbing the same heat that would be absorbed by water vapor if water vapor was all by itself. It should be considered great news. Okay, we don't have to eliminate cows. We don't have to stop eating meat. We don't have to stop using fertilizer. And if we did, it would make no difference because the same amount of radiation is going to be absorbed by water vapor instead of methane or nitrous oxides. So if all the methane was taken away and all the fertilizer was taken away, water vapor there would be no change because water vapor would absorb all of that radiation, and it would still be a total of 90% of it being absorbed in those wavelengths that are of concern. And so this should be great news because we don't have to do these extreme things to try to change the climate. Okay, we don't have to eliminate cows, we don't have to stop eating meat, and we don't have to stop using fertilizer. Okay, and you can imagine this should be great news. I know I keep coming back to this, and I know I keep repeating myself, but I can't stress enough. Look at the nitrous oxide, look at the methane. If those and the water vapor actually added together, this would be filled up. They don't. They don't because it doesn't work that way. Okay? If there's 10% that can get through water vapor, and there's this region that can get through methane and this region to get through nitrous oxide, and we still have 90% in the total. It means if you take away methane from cows, you take away nitrous oxides from fertilizer, you're still going to get the same amount of heat that's absorbed because water vapor will still be in the atmosphere. We want to be thorough about this, so what about the other wavelengths? We talked about the 8 micrometer wavelengths. Well, what about methane near the 3.5 micrometer wavelength? And what about nitrous oxides near the 4.5 micrometer wavelength? We'll take a look at that. Here's methane near the 3.5 micrometer wavelength right here. Okay, there's methane near the 3.5 micrometer wavelength, and here's nitrous oxide. This is the one near the 8 that we just talked about that's overlapped by water vapor. Well, if we take the nitrous oxide, and this one's around, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is not a dot right here. So this would be 10, 9, 8, 7, 6, 5, 4.5. So here's nitrous oxide at 4.5. Okay, if we follow that up, what do we see that's also absorbing the same radiation? Carbon dioxide. Okay, so carbon dioxide overlaps it here. Now there's one more thing I want to show you. If we follow it all the way up, there's very little radiation coming off the earth at that wavelength. Okay, so there's very little heat to intercept anyway at that wavelength. That's from fertilizers. Okay, if we drop it back here, this is about, let's see, 1, 2, 3.5 micrometer wavelength. We've got another bump of methane right here. If we follow it up, again, overshadowed by water vapor. Overshadowed by water vapor. And if we follow it all the way up, literally nothing coming off the earth at that wavelength. Literally nothing. So there's no heat to absorb if there's nothing coming off the earth at that wavelength. Just made this point. Look at the top of the chart. Almost no radiation at that wavelength being given off by the earth. There isn't any radiation to absorb at those wavelengths. So in the lab, yeah, methane will absorb those wavelengths, and nitrous oxides will absorb those wavelengths. But if there's no radiation coming off the earth at that wavelength, it doesn't matter because there's nothing there to absorb. So if the methane was removed, it would still be absorbed by water vapor again. We saw that water vapor overlaps the methane, and CO2 overlaps the nitrous oxides, even at those wavelengths where there's very little radiation coming off the earth. It's still overshadowed by both carbon dioxide and water vapor. Here it is again, just to show you this. This bump was the primary concern right here because there is radiation coming off the Earth at these wavelengths, but you can see that both of these were overshadowed completely by water vapor, and we're still 90% of it. It didn't add up to 100%. There was still 90% being absorbed, and 10% was still getting through, even with methane and nitrous oxide present. Water vapor and the total are the same. Up here at these smaller wavelengths, you see the nitrous oxide being overshadowed by carbon dioxide, okay? And you see the methane bump here being overshadowed by water vapor. And when you follow these two bumps up, you see almost no radiation coming off the Earth at those wavelengths anyway. All right, the 2.5 wavelength, micrometer wavelength where methane absorbs is produced only at high temperatures, which are the temperatures in a forest fire. So there's a reason that the Earth isn't giving off those wavelengths, because those wavelengths reflect a higher temperature. And that temperature for methane is the same temperature in a forest fire. But what happens if methane encounters fire? Okay, methane burns and changes into water vapor and CO2. So there's no more methane. If you raise that, if you have those temperatures on Earth, you have a forest fire. And if you have a forest fire, it's burning the methane and there's no more methane. So those wavelengths are not the concern. The concern would be the 8 micrometer wavelength, but I wanted to cover those wavelengths just to be thorough. Okay, methane burns into water vapor and CO2 at that temperature in the presence of oxygen. So methane can only absorb radiation at that wavelength in a lab where it can't catch on fire. This wavelength right here of methane, this is about the same temperature as a forest fire. Now, the reason the sun gives off radiation, sends it to us at these really short wavelengths in the visible light range is because the sun is so hot. The sun is so hot, these represent temperatures on the sun. Okay, now when they get to us, obviously we're not burned by them, because after they come off the surface of the sun, they spread out. And so we get these wavelengths, but we don't get them like we'd be getting them if we were standing on the surface of the sun. But they do represent the temperature at which they're given off, and so the sun gives them off at this high temperature. When you come down to this temperature, this temperature where methane is, that's about forest fire temperature. Okay, nitrous oxide is a little bit less than that, but it's absorbed by carbon dioxide as well, and there's not much energy given off by the Earth in that temperature range. Up here in the other temperature range for methane, again, that's more like a forest fire. So to sum it up, if we took away all the methane and all the fertilizer, the same heat radiation would be absorbed by water vapor instead. Okay, so the thing that they're worried about is because the lab shows that methane absorbs this energy, this heat energy that's coming off the Earth, and it shows that fertilizers, nitrous oxides, can absorb this radiation. But the fact that water vapor absorbs the same amount of radiation and more of it shows that, and the fact is they don't add together. The effects don't add up. It's an overlapping effect, so that even if we took away the methane and took away all the fertilizer, the same heat radiation would be absorbed by water vapor instead. With or without it, about 10% gets through at the 8 micrometer wavelength. So getting rid of cows and fertilizer will make no difference in the heat energy absorbed. This is not going to change the climate at all. If you get rid of cows and fertilizer, you're going to do nothing for the climate. Even if you did the whole Earth, you would do nothing for the climate. It's going to make no difference as long as water vapor is present in the atmosphere. If water vapor is present in the atmosphere, that radiation, that heat is going to be absorbed as it comes off the Earth. And only 10% is going to get through, whether you have cows, whether you have fertilizer and water vapor, or you just have water vapor by itself. this should be great news, okay? Because it means we don't have to do these drastic things like getting rid of our cattle or getting rid of our fertilizers that we use to produce food. This should be great news, okay? Now, what's the reaction going to be if more and more people understand this and more and more leaders understand this? Is this going to make the experts happy? Okay, and that's the big question, and actually that will expose what their motivations really are. Okay, are they going to be happy when they hear this, or what's their reaction going to be? And I implore you to share this with as many people as you can, not because I want a famous video, but because I want the truth to get out there. I want people to understand we don't have to slaughter all the cows. We don't have to get rid of using the fertilizers. It's going to make absolutely no difference as long as water vapor is in the atmosphere. And if we ever get to a point where water vapor is not in the atmosphere, we're all dead anyway. Okay. But water vapor is going to be there whether we take away the fertilizer and take away the cows or not. And that water vapor is going to absorb the same amount of heat. Fertilizer and cows are not going to add anything to the heat that's absorbed by the atmosphere. Okay, so I hope this video is clear. There is absolutely no threat to the climate from cows or farming, methane, or fertilizer. Okay, it will not change the climate at all as long as water vapor is present in the atmosphere. Our greatest environmental threat is not climate change. Now I'm going to get into more of that in further videos. I'm going to show you how the climate actually works and the physics behind it, and those physics will apply to Earth, Venus, Mars, and Titan. And regardless of the gases in the atmosphere, the physics determine the amount of heat that those atmospheres can hold. And I will explain to you how that happens. But for now, I just want you to know there is no threat to the climate from cows or farming, methane, or fertilizer, even by these charts that are put out there to show you what radiation each greenhouse gas absorbs. So if you understand the chart and you can look at that chart and you can see what's going on there, you can realize there's no threat from methane or farming or fertilizer or cows, okay, as long as water vapor is present in the atmosphere. That heat is still going to be absorbed, whether it's absorbed by just the water vapor or whether it's absorbed by all three gases. So our greatest environmental threat is really not climate change, it's the loss of farmland. Okay, that's the greatest threat to people, is the loss of farmland. And the greatest threat to nature as a whole and people as part of nature is well-managed natural habitats. So our loss of natural lands, natural habitats, biodiversity is a much greater threat than anything from climate change. And the loss of farmland is a much greater threat to humanity itself. So what we need is we don't need less farming, we need more farming, and we need to integrate human activities with the natural world, and human business, human buildings, human houses. Those things need to be integrated with the natural world so that the natural world can expand and so that biodiversity can be preserved and expanded. So those are the greatest environmental threats that are out there. And there is no threat to the climate from cows, farming, methane, or fertilizer. That's the main point of this video. So thank you for watching. I know I repeat myself over and over again, but it can't be emphasized enough, and it needs to be shared with people. You need to look at these charts. You don't have to look at the exact chart I used. There are other charts out there that will show you the wavelengths and the amplitudes of energy that are absorbed at each wavelength by each greenhouse gas, and you will see that the overlap, you'll see that the overlapping and the overshadowing of water vapor at each of those wavelengths. So thank you for watching this video and for listening to it. Cows and fertilizer are not a threat please share this video and its contents with anyone you can, anyone who will listen, especially those who are in leadership. Let's not slaughter the cows for no good reason at all. Thank you.